Hi guys, welcome to the lesson of partial differential equation. So in the previous lesson, we discussed about the general Fourier series and its convergence, right? So now we are going to discuss half-range Fourier series. So if a function is defined in an interval 0 to L, then the Fourier series is defined by f of x is equals to a naught over 2 plus sigma n runs from 1 to infinity a n cos n pi x over L plus b n sin n pi x over L. So the idea is same for solving the series. The coefficients are same. In this case, a naught will be equals to 2 over L and integral 0 to L f of x dx, right? And an is equals to 2 over L integral 0 to L f of x cos n pi x over L dx. Bn is equals to 2 over L integral 0 to L f of x sin n pi x over L dx. Right, so we'll solve some examples. Let's say if a question is given that find half range Fourier series. Half range Fourier series of the function f of x is equal to x squared defined in the interval 0 to L. So the series will be f of x is equal to a naught over 2 plus sigma and 1 to infinity a n times cos of this angle and b n times sine of this angle, right? So a naught will be equals to 2 over L integral 0 to L x squared. When we will solve this, we will get 2 over L times x cubed over 3 from 0 to L. So we will get 2 over 3L times L cubed. Finally, we will get 2L squared over 3. All right, so this is the idea. And for an similarly, we can solve for an in the similar manner, and it's 2 over L integral 0 to L x squared cos n pi x over L, right? So from this we can calculate an, and from this we will calculate bn, and the general form that we will get will be a naught divided by 2 plus sigma n is equals to 1 to infinity a n cos n pi x over L plus bn sin n pi x over L. All right, so let's move to another example. Let's say we are given with a function e power x, and it's defined in this interval, and we are asked to find the half-range Fourier series. So you can see that the half-range Fourier series is given by this series, right? So we'll solve it. We'll find a naught, an, bn in the similar manner, and then we will write the final form. That is, we'll write in the series form, right? So you can solve it. And now for this example number 3, f of x is x squared from 0 to 3. It is defined in this interval. So the series will be like this. The angle is now n pi x over 3. And here it will be 2 over 3 because L is equals to 3 in this case. So we will find a naught an, and similarly we can find bn. Then the final answer will be f of x is equals to the series. Then we move to the example number 4, that is a piecewise function. And this is the point of discontinuity. And here we can see that L is equals to 2. This is L, right? So the function is basically from 0 to 2. Here you can see that the lowest limit is 2 and the highest limit is, the lowest limit is 0 and the highest limit is 2. So now we can solve it by piecewise integrals. So it will be 2 over 2. This is L. L is equals to 2. And first we will integrate 2x from 0 to 1, plus then we will integrate this function from 1 to 2. We will add both these and we will get a naught. Similarly for an, 2 over 2 integral 0 to 1 2x cos n pi x over 2, then 2 times 2 minus x times cos n pi x over 2. And for bn, again we will integrate this piecewise, right? And similarly, you can see that example number 5. You can try it yourself. In this case, L is equals to small l. So you can solve it for a naught, an, and bn. Now, in example number 6, we have a modulus function. So we know that for modulus function, if it's a odd function, like we know that mod of x is an odd function. So we will break this function, right? And we'll make it piecewise function. And the interval is from -1 to 1. So now we can break this interval, because from -1 to 0 it will be -x squared, because x, this means that this function means that x times -x when x is from -1 to 0, and x times +x when x is 0 to 1. So we'll break this function like this, and then we can apply the half range Fourier series, and we can see that L is equals to 1. Here it's L, right? So in this case, you can see that we are not doing b minus a. So this is L, right? So it will be 2 over 1 integral of -x squared from -1 to 0, and then x squared dx from 0 to 1. Similarly for an and bn, we can follow the same procedure as we did in the previous examples. Then we will generate a general Fourier series for this function after finding a naught, an, and bn. This is also an example of a piecewise function, and we can see that L is equals to 2 in this case. So the Fourier series generated by this function will be a naught over 2 plus sigma n to 1 an cos n pi x over 2 plus bn sin n pi x over 2. And we have to integrate for a naught, an, and bn piecewise, right? First we integrate 1 from -2 to -1, then 0 is 0, and then 1 from 1 to 2, right? And then this is example number 7. F of x is cos x. That's equals That's cos x, and it's defined in the interval 0 to pi over 2, right? So now L is equals to pi over 2. So here this is pi over 2. So it will become 2nx. Pi will cancel with pi. This 2 will be multiplied by nx when we will simplify this. And then the Fourier series will be generated like this. Then a0 is equals to 2 over L. L is pi over 2. 0 to pi by 2 cos x dx. All right, so this will be sine x. 0 to pi over 2. And it will be 4 over pi, right? So this will be equals to 4 over pi times sine pi over 2 minus sine 0. So we will only left with 4 over pi because sine pi over 2 is 1 and sine 0 is 0. All right, so in the similar manner, you can integrate this function. First, you have to transform this function from product form to sum form by using the trigonometric identities, and then you can solve this function. Then again, cos x into sine 2x, it will break by cos alpha sine beta, and you can write it in the sum form. So you will get, you can then easily integrate, or I can write it like this: 1 over 2 times sine alpha minus beta plus sine alpha plus beta. All right, and then it's easily integratable. If you will break this, so what we will get is 4 over pi times 1 over 2 into the integral 0 to pi over 2 sine x minus 2nx plus sine x plus 2nx. And we can see that now it's easily integratable, right? So these are some examples for half-range Fourier series. So you can solve these examples for good preparation. Thanks for watching our lecture. We'll meet soon in another lecture on well-posed ness and superposition, right? Goodbye till then.